more calculations, centripetal force, letters C and D. So this worksheet, do number 1, 2, and 3. If you want to do number 4, you could. That's a little bit more advanced. But anyway, this is not bad. So this will finish up the first section of this chapter, which is a short one compared to the next two. And we'll have a quiz on this sometime after this stuff. Okay, so here we go. All right, so letter C. This is all going to involve the same equations we've been seeing. You know, centripetal acceleration is v squared over r. Or centripetal acceleration is 4 pi squared r over t squared. And also that friction force is, not friction force, I said friction. Centripetal force is equal to mass times the centripetal acceleration. So you already know that. Just put a little c there and there. I was thinking about there's going to be a friction problem in here. And anyway, if there's friction involved in a problem like this, the friction force is the centripetal force. I'll talk about that as we go on. Okay. In fact, it's the first question I see right here. It says, letter C. So this is right before, in your notes, it's not 7.1, but it's before, the 2 pages before 7.1. Okay. 7.0, C is, I don't know why. I guess it's a long story, but oh well, why I named it that. I could have just let that be 7.1. I guess this is the beginning of the real official planetary motion chapter, but then you got to know some of this beforehand, and I had to throw this in. A 45 kilogram merry-go-round worker. So we know the mass is 45 kilograms. Stands on the ride platform 6.3 meters from the center. So a merry-go-round, you got the horses and all that. So I'll just draw it like this. You can imagine that it's like this. Here's the merry-go-round, and there's, the horses and all, and someone is standing. I don't know, the workers don't usually stand on the merry-go-round, but whatever. But he's standing there. But, from the top, if you could be like an aerial view, like be above in the ceiling looking down at the merry-go-round, well, if it had no cover on it, then the person will be sitting right there, and it says they are 6.3 meters from the center. So maybe they're right here, 6.3, and that would be the what? The radius. Okay, that's where they're sitting. Right there. We'll just say, here he is, or she, or whoever it is, 6.3 from the center. Okay, right there. All right. Now, I know, for your picture, you could just make the whole thing, the circle be 6.3. I mean, you could just say, all right, that's 6.3. I don't think it's going to matter in these problems. And there could be a problem where that might be mattering. There might be somebody else standing somewhere else. But okay, let's just see what it does. Oh, and it says it's a woman. Her speed as she circles is 4.1 meter per second. So her speed, velocity, 4.1 meter per second. Okay, as going around, that's the velocity, that's her mass, and that's the radius right there. So you got radius, 6.3 meter, mass, 45 kilogram, velocity, 4.1 meter per second. Hopefully, from that, you already can look up here and say, oh, I can find a lot of stuff already from that. There's another equation. C is 2 pi r. If you wanted to know what is that circle around the merry-go-round, from where she's standing, if she were to circle, it didn't say she's on the edge necessarily, but they didn't ask that. They didn't ask it. All right, number 1. What force of friction is needed to keep her from falling off the platform? Now, this is more advanced because you're jumping way ahead. Wait a minute. What force of friction to keep her from jumping off? Well, I guess I just said it right before on the video. I went thinking that was, it was more of a coincidence. I glanced at it. Remember, on the circular motion, when they talk about friction force, it's pretty much always going to be the centripetal force. And it will be. And I'll tell you. Remember, the only reason, I still have it, okay? The only reason why this little ball, the red ball, is moving in a circle right now, why does it stay in a circle, is because there's a force called a centripetal force, a force pulling it toward the center. That force is the rope. This rope is keeping it pulled to the center. Kind of weird, but it is. It's keeping it pulled to the center. I mean, you might not think of it that way, but it is. Because if I were to cut the rope, it would no longer be in a circle. It would just go in a straight line. Okay. So something must be keeping her in the circle if she's on the merry-go-round, and it has to be friction. To prove that, you can go to a merry-go-round, and I wouldn't do it, of course. It would be dangerous. But just say if you had, well, actually, this could be a real life situation. Let's just say that somebody, what would be a really bad thing to spill? Well, usually we think of water or a milkshake. Maybe a milkshake could be really bad. If they spilled ice cream down on the merry-go-round and they didn't see it and they were standing on it as it goes around, you might just slide off. You just slide right off the merry-go-round because there's no friction holding you in place there. You don't want to try that, okay? You don't want to try it on your own. I mean, if there were an oil spill, you have to be even easier, but you don't like to spill oil on the merry-go-round, but oh well. Okay, so here we go. So the friction force will equal the centripetal force, okay? We know that has to be true. So let's find the centripetal force. Centripetal force is mass times centripetal acceleration. Well, we have her mass, but we don't have the acceleration, but we can find the acceleration from that equation. So you got to go all this. Sometimes the good thing to do might be, if you're not sure where to start, just do what you can do. Like, I know the velocity and I know the radius, so let me find the acceleration. Because chances are, if you just do this, I'll probably, on a quiz, I'll probably say, I probably won't just jump to that one. I mean, I might. There could be like a bonus question where I ask you, what is the friction force needed to keep her from falling off the merry-go-round platform? That involves several steps. I probably will ask you each step, one time on the test, but I might possibly give like a bonus question. Okay, so anyway, here's how it goes. First you got to find the acceleration, and that's going to be 4.1 divided by the radius of 6.3 meters. So I can just do that horizontally here. Oh, it is squared. Don't want to forget that. And it's not squared there. I put squared there, sorry. 4.1 meters per second squared, okay, over 6.3. So 4.1 squared is like 16.81 divided by 6.3, 2.7. So that's the centripetal acceleration. Okay, now, so that's the first thing. The second thing, we're doing part one of this problem. So we know the friction force will equal the centripetal. First, we got to find the acceleration. Now we have acceleration, we can find centripetal force. And that'll be her mass, 45 kilogram, times acceleration, 2.7 meter per second squared. And 45 times 2.7 is 120. Well, we'll just say 120 for sig figs if I want to be exactly right. You got 121, you'll be okay, or 122, but really it should be 120 newtons. Okay, that's your centripetal force. So, since friction force would equal 120 newtons. That is number one of letter C, part one. Now, part two, they say, what is the minimum coefficient of friction needed or necessary to keep her from sliding off the merry-go-round? Okay, I did one like this already in an earlier video. Don't let the word minimum scare you, but I'll tell you why in a minute. But just what is the coefficient of friction needed? Now let's remember the friction equation. I didn't put it up here, but I'll put it right here. The friction force is the coefficient constant times the normal force. Now, on these problems, she's standing here and it's horizontally on a circle. Now, I know there are some carnival rides that you're this way, but then it goes up and then it turns you like at an angle that way, all right? And in that case, if you're standing on a platform, okay, but then if you angle it, now your friction coefficient is going to be different. It's going to be not your friction coefficient. I'm wrong about that. Your normal force is going to be different, okay? But we're not going to worry about that. Normal force will just equal your weight in this problem. On all of these, I'm not going to do that to you. That would be ridiculous. Now in college, maybe you'll get some professor that might do something like that to you. And hopefully he'll only do it on a bonus problem and not on the main one. But your normal force will equal the weight. So that means mg, which will be 45 kilograms. Now make sure you know that g is 9.81. So can you read that? Oh, you can barely. There it is. Okay. So 45 times 9.81 is 441 newtons. Or actually it can be 441 newtons. That's your normal force. Now, so if the friction force, come over here, this is all part 2. Friction is 120 because it's equal to that. Okay, that was part 1 actually. But okay, so the normal force, here's the equation for friction. The normal force will have to be mg, 441 newtons, okay? I'll take this number and bring it over here, 441 newton. I don't know the constant of friction, but I do know the friction force is 120. 120 newtons equals the constant times 441. So now you just divide them both by 441. Algebra. And it is 0.27. We'll just go with 27 because it's 2 sig figs. 0.27 is the coefficient of friction. That is all you have to do for that one. That's your answer to that one. Okay. So, I'm trying to not stand in the way if you need to take a screenshot or whatever. All right. Now, there's one more crazy problem. And these are all great. They're like, go to the amusement park. In fact, I know that now we're closed because of the virus closure, but every year, Six Flags Magic Mountain, they hold these things called physics days. And yes, we take, I've never gone on one, but teacher would take students there. They get to ride the rides and all that. And they do experiments on them too as well. And there's some of these that are safe. I mean, you're not going to jump off anything or anything like that. But a lot of these are safe experiments. But it's really neat, amazing. I've never done that, but also another reason why we've never done it is because it costs a lot of money. You pretty much, they say, whatever the price to go to Magic Mountain is, it's usually like, it's like $5 less or $10 less if you have, go with the group, a school group. It ought to be a lot less, shouldn't it? So I don't know. If we could ever get a donation or a grant, that would be a great thing. Wouldn't that be amazing? That'd be like the best field trip you ever took in your life. And we do some physics too. Okay, letter D. Okay, it says here, a carnival clown rides a motorcycle down a ramp. So they go down a ramp and then around a vertical loop, upside down, which has a radius of 18 meters. So the loop is 18 meters. No decimals. Okay, 18 meter. That's the radius. Okay, so there's a little carnival clown. I don't know how to draw him riding on a motorcycle or whatever he's driving on, going down. That looks like a weird, well, I don't know how to draw the motorcycle, but I'll do something like that. So it goes there, and then and he goes all the way around. Boom. Okay, this is a fun one, isn't it? Just like any ride that goes upside down roller coaster. Now it says, here's a scary kind of question. What is the slowest speed the clown can have in order to round the loop and not fall down? Oh boy. So when you go down, when you get to the bottom, you're going to be accelerating all the way down the ramp. But right at this point, you're not going to be accelerating anymore right now. Remember Newton. Now you're going to keep going straight. Friction is the only thing slowing you down then. But you're going to keep going straight. And now, if you're going fast enough, you're going to make the whole loop. If you're not going fast enough, I guess you'll go up here and just boom, just fall down or something. Or go up here and fall down right there. So you have to be going, what speed? Minimum speed. Now you care about minimum. In fact, this is a good example to tell you why do we care about the word minimum coefficient and all that. Well, when it says minimum speed, it means this is the slowest you can go and still make the loop. If you're going faster, then that's even better, okay? But you don't want to go slower than that. Same thing with the friction. You don't want to go lower than that coefficient, or then you're going to slide off, okay? But if you're going, you can be that number, that velocity, or that coefficient, or higher, and you're okay. If you have that much friction or more friction, you're good. This speed or a higher speed, you're good. Okay, all right, so what's the speed going to be? Now, for this, let's look at all of the equations involved. We know that somewhere we're going to use this one. AC is equal to V squared over R. We know that if we know the acceleration, then we know the radius, we can find the velocity. And you know what? We do know the acceleration, and you might not realize it. But this is kind of a little technique you'll remember anytime you're going upside down. Think about this. Your acceleration, when you're riding on this thing going upside down, you at least have to match the acceleration of gravity, right? What if you were just up here at the top and not moving at all, and you drop something off the bottom there, okay? Or if he were riding off the ramp up here, or off the top of the loop down, what will be his acceleration going down? It would be gravity 9.81. In fact, I'll just put acceleration of gravity 9.81 meters per second squared. Gravity is pulling you down 9.81. So when you're circling around, you need to at least have an acceleration of 9.81. You need to be going fast enough so that your acceleration is 9.81. And if that's the case, you'll make the loop. Okay, so actually that's the only equation we need here. And we didn't even need his weight or anything there, his mass. So to equal 9.81, what velocity is needed squared if you are going around a loop with a radius of 18 meters? All right. So 9.81 times 18 is 177. And then equals v squared. So now get the square root of both of those sides. Square root of that, square root of that. It looks like 13. Just like, I guess just 13 only. In fact, that could have been just 2 sig figs. And you don't really have to worry. I know sig figs in my AP class, I'm always just, everything is sig figs. You got to be. But I do it here a lot. And I might not always say it, but I'm not counting off for you guys for it right now. On a written test, I would, but if we're doing things online, A, B, C, D, I wouldn't really know. I'm not really trying to get you with that much. Okay, at all, really. 18. So 13 equals the velocity. So 13 meters per second. And 13 meters per second is almost about 29.7 miles per hour. So 29.7. So if you're going 29.7 miles per hour, you're going to make the loop okay. Okay, or 30 miles per hour, or anything higher than that, you're all right on the vertical loop. But if you're not going that fast, you're not going to do it. Like, you can't run that fast. If you were to run down the ramp, you're not going to be able to do it. You're not going to go back the loop. I mean, you'll probably slip up right here. The worst thing would be going is you go all the way up to there, but then there you just start to fall down. That would be worse. Maybe you land here at least on that side. Let's hope. Okay, so that is it. Now, I can't think of any other question to ask you there. I could just make up one thing. Why in the world do you stay in a loop? And this makes it it's very easy to understand. You're going so fast that you're going in a circle because of the force as you collide against the force that you have when you're going against the track. In fact, I once told people to think of it this way. When you see a loop, it does not look like this. What I'm drawing, like a stop sign, is like an octagon, right? But imagine if it were an octagon. This kind of explains it to you. Really at the very microscopic chemistry level, if you could zoom this curve up, none of the curves are really perfect curves. They're all going to be rigid. They're all going to be like this. If you can see like a microscopic view, they look like this. They're not really curved at some point. So the point is, if there's a little ball rolling, if that ball rolls and it hits this side, what's it going to do? It's going to hit this, and it's going to boom. It's actually, when it hits this, well, actually I should make it larger to make it really clear to you, because it would in perspective. When it hits there, it's going to bounce it. This is going to bounce it that way toward the center. It's going to hit there, and it's going to hit it towards that way. Now it's not going to bounce. It's going to just go up the ramp this way. It's going to hit that side, which hits it toward the center. Then that side toward the center. So whenever you are rolling, the ball is rolling along, it's always getting, when it hits the track, it's always getting steered back toward the center. That's why it will always be in a circle. Now, we don't see that here. So I don't know. That's just a little thing that I think about sometimes. It makes more sense here. If I'm running into that, yeah, then boom, of course I'm going to have to go up because it's going to lift me up. It's going to be lifting you that way, lifting and so forth. All right. Okay, so do number 1, 2, and 3. And I guess there must be at least one question in there that might look like one I did on the past videos. But if not, you can ask me about it in the class lesson. All right, but I'll see you later on.